Now, I already mentioned before that optical isomers differ with respect only to their interaction with polarized light and with other chiral materials. We can determine the extent, that is magnitude, of the rotation and sign of rotation, whether rotation is clockwise or counterclockwise. And we determine that using an instrument called polarimeter. There is video on YouTube, and I won't go into details over it, how polarimeter works, but I posted already a video so you can see that. What is important about rotation of polarized light is that since enantiomers differ only with respect to properties that are chiral, they differ only in the sign of rotation of polarized light. So one enantiomer rotates polarized light to the right, the other one to the left. But they don't differ in magnitude. So since they are mirror images of each other, then they differ only in properties that are mirror images. That means sign of rotation, the right or to the left. And we also designate rotation to the right or to the left as plus to the right, minus to the left, or levorotatory to the left, dextrorotatory to the right. That also means that, let's say, if one enantiomer rotates plane of polarized light by 15 degrees to the right, then opposite enantiomer will rotate plane of polarized light by exactly 15 degrees to the left. And we will designate that one enantiomer rotates plane of polarized light by plus 15 degrees and the other one by minus 15 degrees. And it's going to be exactly. So again, in another example, if let's say one enantiomer rotates plane of polarized light by, let's say, a few hundred degrees, let's say 455 degrees, plus 455 degrees. Enantiomer will rotate plane of polarized light by exactly minus 455 degrees. It's not going to be approximate or close or something like that. It's going to be exactly that, because the number, the magnitude is not chiral property. Also, to determine rotation, we need to carry out at least two measurements, because as you know, a fourth circle has 360 degrees. And so rotation could be, of course, since way we see rotation, we can see actually 180 degrees one way or 180 degrees the other way. So we need to carry out at least two measurements with two different concentrations. And then from that relationship, we can see by how much light is being rotated. Because rotation of 5 degrees, let's say plus 5 degrees, could be plus minus 365, not 5, but 365, or something like that, because it could be full circle plus another 5 degrees, so on. So that's why we need two or more measurements, minimum of two measurements at different concentrations to figure out the actual extent of rotation. And we report rotation as specific rotation, which means rotation taken under standardized conditions. So that's rotation is labeled as alpha. It has to be carried out, measurement has to be carried out at particular temperature. Standard temperature is 25 degrees Celsius, and particular wavelength of light. Symbol D means sodium D line. These days we also use mercury green line, which has different wavelength. And of course then alpha is different. So specific rotation under these conditions equals observed rotation divided by path length in decimeters. Decimeter is 10 centimeters. That's traditional. This is traditional definition, and we are keeping it because old chemists or old scientists were using 1 decimeter, 10 centimeter long tube. Multiplied by concentration, and concentration is given in grams per milliliter. Again, old units these days, if you were to do it these days, it would probably be 1 centimeter, and molarity would be moles per liter. Now, individual enantiomers rotate, of course, plane of polarized light by their own specific rotation. But if we have equal mixture of two enantiomers, then one enantiomer will rotate plane of polarized light to the right, the other to the left, by exactly the same amount. So they will compensate each other's rotation, and racemic mixture will not rotate plane of polarized light. So racemic mixture has rotation of 0. But racemic mixture is still chiral. It's mixture of two chiral compounds. And so racemic mixture has the same property as achiral compound. Achiral means non-chiral. Compound is not chiral, in that it doesn't rotate plane of polarized light, but for different reasons. Achiral compound, that's its inherent property, that achiral compound does not rotate plane of polarized light because it's not chiral. In case of racemic mixture, we have two chiral molecules, two chiral compounds, two chiral components, and we can separate racemic mixture into the individual components that would rotate plane of polarized light. We indicate racemic mixture as plus minus or DL. Sometimes when you're buying food supplements or something like this, like vitamin E, you may find racemic mixture DL. That's actually not good. You should be buying like vitamin E, pure vitamin E, like D, because the other one is not vitamin, so you don't really want to consume that. So those are two extremes. We could have pure enantiomer, or we can have a racemic mixture. But we could have anything in between. We could have a mixture that has more of one enantiomer than the other, but it's neither racemic nor pure, not pure enantiomer, not racemic mixture. And then we talk about optical purity of that mixture. Optical purity is experimentally determined quantity. Optical purity equals observed specific rotation divided by specific rotation of the pure enantiomer multiplied by 100%. And so optical purity is expressed as purity in percent. Enantiomeric excess is the ratio of the amount of excess of predominant enantiomer over the minor. So if you have two enantiomers, P and Q, I use these two letters because they are mirror images of each other. So enantiomeric excess is P minus Q divided by total P plus Q. Optical purity and enantiomeric excess are identical numbers. Optical purity is something we determine experimentally. Enantiomeric excess is theoretical explanation, because basic explanation is that observed rotation is due to excess of the enantiomer that is present. So let's say if we have MSG, food additive, that has optical purity of 80%, we would take that sample of MSG, determine its optical rotation, find its 20.4. Pure enantiomer would have 25.5. So optical purity is 80%. What it means? It means that plus enantiomer is in 80% excess. And that's what is responsible for rotation of polarized light. Remaining 20% does not rotate plane of polarized light, which means that remaining 20% is racemic mixture. Racemic mixture is half of each enantiomer. One half left rotating, the other half right rotating. Which means if 20% in this case is racemic mixture, we have another 10% of plus enantiomer and another 10 and remaining 10% of minus enantiomer. So we have total of 90% plus and 10% minus. And that could be exam question, how much of each we have. And this shows you calculation. So on the test, you may have to do one of these calculations. Numbers will always be such that calculation is really easy, really trivial. Probably in this case, I wouldn't give you 20.4 and 25.5. I use 25.5 because that's the actual number. On the test, I would probably give you 20 and 25. So that it's really easy to do the calculation. So you may have to do calculation of optical purity given given magnitudes of rotation, or enantiomeric excess given the amount of one enantiomer, because from one amount of one you can figure out the other, what is balanced to 100. If one is present in 15% amount, the other one must be 85%, and then from that you can do all the other calculations. Or you could be given an enantiomeric excess and how much, what is the rotation or how much is total or something like that. One of those questions. Okay, let me see quickly if there are any questions. No, okay. Now, if isomers have more than one chirality center, then each chirality center would give rise to two isomers. And so a molecule with m chirality centers would have maximum of 2 to the power of m isomers. If there is symmetry present in the molecule, then number of isomers could be fewer than that. This is Van 't Hoff rule. And if you think you have seen this before, you have, because it's the same Van 't Hoff rule for number of double bonds. Each double bond could be responsible for E, Z, or cis trans pair of isomers. And so the rule was 2 to the power of n. And here I'm using m just to be different from n. And you'll see we need that in a minute. We need different letters in a minute. So it's 2 to the power of m, but it's the same formula. And you have seen before with double bonds, if symmetry is present in the molecule, if you can find plane of symmetry, then number of isomers is fewer than maximum number. And so you have to be able to identify that to correctly determine number of isomers. If compounds have both double bonds and chirality centers, then number of isomers is 2 to the power of n plus m, because each double bond could give pair of isomers, stereoisomers, and each chirality center another pair. And so you add those two numbers. You use sum of those numbers. Two isomers that are stereoisomers that are mirror images of each other are enantiomers. But those that are not mirror images of each other are stereoisomers, also are diastereomers of each other. Correct term is diastereoisomers, but we never use that. We abbreviated that into diastereoisomers. To represent, in this case, enantiomers and diastereomers, we use Fischer projections. They are much more convenient, because then we can see exactly which pair is pair of enantiomers and which pair is pair of diastereomers. It's much more difficult to see that from perspective drawing. You could see it, but it's more difficult. So let's consider 2-bromo-3-chlorobutane. So you can see these two Fischer projections on the left. If you place mirror right here, plane of mirror, you can see that one mirror image reflects into the other. Those are two mirror images, that's pair of enantiomers. If you were to determine configuration of each chirality center, it's RRSS. And so that's another thing. You can see that when you have two chirality centers, then RRSS are pairs of enantiomers. And then on the right, we have another pair of enantiomers. In this case, you can see that halogens are on the same side. And again, if we were to place mirror between them, see one reflects into the other. And of course, now SR has RS as its pair of enantiomers. So you have two pairs of enantiomers. This will be drawing as perspective drawing. So it's a mirror plane, so pair of enantiomers. But two of them that are not mirror images of each other are a pair of diastereomers. So we have one pair of enantiomers and another pair of enantiomers. But any of those from those two pairs, if you take one from each pair and compare them, then they are a pair of diastereomers. Enantiomers have identical physical and chemical properties, except for rotational polarized light. Diastereomers are different compounds. They have different physical and chemical properties, different boiling point, different melting points. They may have different solubilities, different index of refraction, so on. When two chirality centers are next to each other, as in previous example that we have seen, 2-bromo-3-chlorobutane, then those are called contiguous chirality centers. Remember, it's contiguous, not contagious. Contiguous chirality centers next to each other. And isomerism is called erythro-trio isomerism, after carbohydrates, erythros and trios. We cover those quite a bit in biochemistry course. So erythros in Fischer projection has two hydroxyl groups on the same side and trios on the opposite sides. So after this, all the stereoisomers that have two chirality centers next to each other with identical or similar substituents on the opposite sides in Fischer projection are trio pair, and on the same side erythro. So for the test, you must know which one is erythro, which one is trio pair. So trio opposite side, erythro same side. And again, from Fischer projection, that's easy to see. A little bit more difficult is to see that from perspective drawing. So in general, I expect you only to know that from Fischer projection. I don't expect you from perspective drawing. If chirality centers are not contiguous, they are not next to each other, then we still have up to 4 possible stereoisomers, 2 to the power of 2, 4, but we cannot use erythro-trio designation. We can only use RS, no longer erythro-trio, because they are not next to each other. You have to be able to identify chirality in cyclic compounds. So again, look, are cyclic compounds chiral? And first thing to do is what you already should know. And that means look at carbon that you suspect to be chirality center, draw the line to cut ring into 2 halves, 2 equal halves, and see are halves identical or different. And in these cases, these 4 examples, 2 pairs of compounds, these are not chiral compounds. There are no chirality centers. These are cis and trans isomers in first case of cyclobutane, and cis and trans isomers of cyclohexane. But there are no chirality centers because 2 halves of the ring are identical. So as you can see, 1,3 disubstitute cyclobutane has no chirality centers because it has plane of symmetry, that line. And 1,4 disubstitute cyclohexane also has no chirality centers, again, because 2 halves of the ring are identical. But if they are not identical, then we have chirality centers. And so in this case, for each carbon, if you were to draw a line going through the middle of the ring, you would see that each carbon is chirality center. And then we have 2 pairs of enantiomers, because we have, in this case, 2 different substituents. So we have, this is cis pair of enantiomers. And if you flip it actually on the side, you will see that that's, in Fischer projection, those will be on the same side substituents. So that's erythro pair. So in cyclic compounds, cis corresponds to erythro. But in cyclic compounds, usually we call them cis and trans pair of enantiomers. And of course, any cis to any trans is related to each other as diastereomers. And in cyclohexane, we could have 1,2 or 1,3 disubstitute compound. And again, we have cis and trans pair of enantiomers. So 2 pairs of enantiomers for a total of 4 stereoisomers. So in cyclic compounds, make sure that you can identify whether there are different enantiomers, whether we have chirality centers, how many, and then how many stereoisomers. Now in compounds that have more than 1 chirality center, but only if there is more than 1 chirality center, then it is possible to have individual chirality centers, but molecule still has plane of symmetry, and then it's not chiral. Such compound is called meso. So that specific class of compounds, meso. It's because they are not chiral, they don't rotate plane of polarized light. They are different from achiral compounds, non-chiral compounds, because they have individual chirality centers. And that's example is here, 2,3-butane diol. Trio is pair of enantiomers. But erythro is not. Erythro is identical compound. That's because there is plane of symmetry going through the middle of the molecule. And again, you can see utility of Fischer projection formulas. Why Fischer formulas are so good? Because if we can draw a mirror plane through the middle of the molecule that reflects 1/2 into the other half then this compound has plane of symmetry and is a meso compound. Meso compound occurs whenever there is symmetry in the model. That's equivalent to symmetry of double bonds, when we could place plane of symmetry to the middle of the compound that had more than one double bond, so one half reflects into the other half, and then cis trans is identical to trans cis, or EZ identical to ZE. Here, RS is identical to SR, because you can number the compound from the top or the bottom. And it's arbitrary which one of them is 2 or 3, because those are two identical substituents. Which in turn means that, of course, on the test, you may have to determine configuration of each of the chiral center. So what you would have to do is determine order of priorities: oxygen 1, hydrogen 4, and then you have two carbons, carbon versus carbon. And then on this carbon you have oxygen, on this carbon hydrogen. Higher priorities are 1, 2, 3, 4. Move substituent 4 to the back, do other rotations, and figure out. But if you recognize compound as meso, you don't need to do any of it. You right away know it's RS or SR. Conversely, that means that if there is mesoisomer, then trio must be RR and SS. And since it's RR, SS, all you need to do is determine configuration of one of them. And then one chirality center, and then the other must be identical. So that's considerable time-saving method, and you need to be aware of it. And of course, if mesoisomer is present, then maximum number of isomers is one fewer. So with two chirality centers, maximum number of isomers was 4, 2 to the power of 2, 4. If mesoisomer is present, then two of them are identical, so maximum number of isomers is 3. 2 enantiomers and meso 3. By the way, this is mesoisomer. So this is chirality center, 4 different substituents, these 3, this 4, and this is another chirality center, 3 different 4 substituents. But each of them has same set of 4 substituents, and that's why it's meso. And there's plane of symmetry going through the middle. So it's identical to its mirror image. So you can overlap. And in Fisher projection, actually it's a mirror image. In Fisher projection, 180 degrees rotation is allowed. 180, you get the same. So that shows that mesoisomer is the same compound. And I mentioned already, meso is third reason why compound may not rotate plane of polarized light. It may not rotate plane of polarized light because it's achiral. It's not chiral. It does not contain any chirality centers. Second reason is it could be a racemic mixture of equal amounts of two enantiomers. And third reason is it could be mesoisomer. Some cyclic compounds could also be mesoisomers. And for that, the best thing to recognize mesoisomer is to draw a ring as planar, even though we know rings are not planar. And when you're making a model, it may be difficult to make a planar ring because you're going to break the model. In this case, for cyclohexane, you may want to make both conformation. It's easier to, because that's more symmetric. Because chair conformation will always appear to be chiral. But when you make both conformation more symmetric, then you will see if mesoisomer is present. You can see cis isomer is meso. So if the mesoisomer is present, it's going to be cis isomer, because that one has plane of symmetry going through the middle. And so 1,2-dibromocyclohexane is going to have only 3 isomers, even though it has 2 chirality centers. Trans pair of enantiomers and cis. Now, sometimes students don't realize that trans pair. And again, I made two both conformations. The trans pair is a pair of enantiomers. They think, well, if you flip one upside down, it's going to be the same one. But no, if you make 2 models and you flip one upside down, you see there is a mismatch. Even if you make chairs match, there is a mismatch. You can't get hydrogens and substituents, bromines to match, hydrogens and bromines. So you may want to play with models a little bit as you are studying to convince yourself of that. So in cyclic compounds, if substituents are identical substituents, 2-bromo, 2-chloro, 2-hydroxy, then trans pair is pair of enantiomers, and cis pair, if there is chirality, cis pair is a mesocompound. And then number of isomers is 1 fewer, so 3 instead of 4. Of course, if we have in some cases 3 chirality centers, then maximum number of isomers is 2 to the power of 3, 8. And if we have 1 mesocompound, then it will be 7. Although you wouldn't get something that complex. You could get 8, like 3 chirality centers and then 8 for the test. But to give you 8 where 1 is meso, that would be a little bit too much because you have limited time for the test. If it were, let's say, 2-hour exam, then maybe. But this is going to be 1-hour exam, so no, it's not going to happen. And finally, when it comes to nomenclature of isomers with more than one chirality center, then we indicate nomenclature simply by determining each chirality center separately. And then, just like EZ, we list that in parentheses before the name, full name of the compound, and we indicate what is configuration of each chirality center. So chirality center 2 is, in this case, S, 3 is R, so 2S3R, 3-chloro-2-butanol. And you should be able to determine that from either perspective drawing or Fischer projection. Make sure that you're familiar with these, with these transformations. Now, one thing you may want to do with these transformations is, if you're working on pen and paper, with Fischer projection, it could get confusing moving these things around, OH, H, and so on. Instead, isolate each chirality center. So draw chirality center as a cross, and then determine priorities. So on that cross, let me see. I'm just going to show you this. I won't be posting this. So you just draw a cross, and then determine order of priorities. And then you find that order of priorities is 1, 2, 3, 3, 4. And so, even though you may have two chirality centers like this, and maybe priorities are different, you draw them each separate. And then you can do easily transformations. If you want 4 to be on vertical bond, you can flip 2 and 4, 1 and 3, and then you end up with, rather than having something with 2 chirality centers where you are flipping them and getting confused. So isolate each chirality center, and so now when you are flipping them, I don't know if it's going to work, but well, okay, that's not what I wanted. 4. It's just giving me 4. Okay, I have to delete them all. But to flip them, you need 4 on a vertical bond because you want it behind the plane of the drawing. So you have to flip 1 and 3. So 1 is going to be so you're flipping 1 and 3 and 2 and 4. So 2. Right. And so you can see that this is R. Right, is it R? No, it's S. It's counterclockwise. Right. Oh, actually, it looks like I wasn't sharing it. I thought I was sharing it. Okay. Enter. Okay, let me share. Okay. Yeah. Okay, so what you do is what you should do is, instead of dealing with one formula, one Fischer projection, where you have 2 contiguous chirality centers, separate them into 2 chirality centers and ignore what are the substituents. Just write down what are the priorities. So simply write bonds in form of a cross for each individual chirality center, and write down priorities 1, 2, 3, 4, and then do the allowed manipulations. So in this case, you may want to flip 4 and 2 and 3 and 1, and simply on paper you simply draw a new formula where you flipped 4 and 2 and 3 1, and now you can tell that 1, 2, 3, ignoring 4, gives you counterclockwise, and it's S. And then do the same thing for the second chirality center. And that's how you figure out for each individual chirality center. Instead of dealing with the entire formula and trying to move all the substituents in the entire formula around, because students get confused when they are doing that. So hopefully this will be in the recording. Separation of enantiomers is something that is associated with the lab. If you carry out labs where you're doing separation of enantiomers, you would need to know this theory. You don't need to know that, so you're not tested on that. So you can stop effectively studying here. You can read the separation of enantiomers. It's an interesting topic, how we separate them. But you're not tested on this, and I didn't see that you're being tested on any other tests, like I haven't seen it on GRE or MCAT or DAT or any one of those other tests. So all those ways of separation. The only other thing is this last page, this one paragraph. Absolute configuration. You not need to know what is absolute configuration. And to put it very simply, when you have two enantiomers, one is R, the other one is S. If you have two bottles and they are mirror images of each other, how do you know which is which? And it's very difficult, but we have ways to figure it out. And that's explained a little bit here. One is to use a special X-ray technique called anomalous dispersion. Anyway, if we can assign configuration to each enantiomer, so if you know which is which, because sign of rotation, plus or minus, is not related to stereochemistry to configuration R or S. So if we have plus 2-butanol, for example, and minus 2-butanol, one is R, the other one is S. We don't know which is which. That means we know only their relative configuration. But if we figure out which is which, then we can designate them, let's say, R minus 2-butanol. That means we know that minus enantiomer is R, and that conversely plus is S. Then we know absolute configuration. So that's what absolute configuration means, that we know which is which enantiomer is which. And the first compound that we determined that was glyceraldehyde, and then we worked from there to figure out the rest. Okay, so that completes this chapter on stereochemistry.